For another. Oh my god, I get loud. I'm sorry. Over screen right now. No, I mean like, I've been missing doing the lab. I'm not missing that. I'm missing doing the lab. I'm gonna have to turn my
All right, let's go ahead and get started. It's good to see everybody. So we'll take attendance. Let me just try to go through that real quick. Where's Alex? Alex, check in with me. And, Bonnie. Where's Thad? Not here. Diamond's not here yet. Then Cassidy, we have one person I don't know. I don't see an unknown face. Hunter. Jeffrey is not here, but check in with me if you're online. Oh, Alex is online, thank you. Sky's not here? I'm surprised Sky's not here. And then, all right. I think I got everybody. So y'all are the survivors, we'll say. I think a lot, there's some self-selection though that goes on. So now we're here, third quarter of chemistry. Let's just go over the syllabus a little bit. Also, I apologize. So your course shell right now kind of looks maybe somewhat of a disaster. Or there's nothing in there, really. So what I'm trying to do is I'm trying to rebuild your course thing from scratch. So yeah, I think I told you, right, the migration Blackboard Ultra didn't work well. So I'm kind of rebuilding it, so that's why you have very little information. So I'll keep kind of filling it in. And then I have to admit that even your syllabus is, what is that? Okay, that was not what I was expecting.
Sorry.
Are you serious? Okay, that's even stranger. Well, I was going to say that your syllabus isn't quite set. I can't believe this is. I feel like it was working all until I try to show you guys.
Why did they make you do it through Concord instead of like a PDF?
It's supposed to be helpful. Okay, all right, I finally got it up. So let's take a look at some of the things. Oh, there you are. Sorry, trying to get attendance officially. And so kind of, one thing I want to point out, so again, I'm trying to rebuild your course shell so that maybe the Blackboard grades will actually function For some reason, I literally tried to program it, and then it kept giving me 200%. It's like, I know how to add to 100, and then it magically, like, gave another 100%. So I don't know why that didn't function. But remember when you're calculating your grades that you have to weight them. So that's what happened last quarter. There were some rough exam performances, and overall, though, I think the grades shook out. Again, I curve everything. And what I look for in the grades is like breaks. And it's weird, but it always happens. But like there'll be a range of smatterings of grades. So it's like those are the A's, there's a weird gap, then those are B's, weird gap, C's. And it always happens. I swear, it always happens. So that's how you got your grade normalized. Again, I was pretty pleased with the grading curve. But just keep in mind that those percentages are where they come from. I have no idea what Blackboard is doing. And this should be a fun quarter, kind of all over the place. So we're going to finish up acids and bases, so keep doing those rice tables. And then rice and equilibrium will kind of follow us to solubility. And then we'll kind of shift and do thermodynamics. So this is more Gibbs free energy. Then we'll shift over to redox. Have our exam, of course, week 5. I'm assuming there's no lab. Like I said, I don't really have the syllabus totally done because we're supposed to do a field trip to the Oregon caves, so I'm still waiting to hear back from them. I'm hoping that they weren't influenced or impacted too much by the budget cuts. So hopefully we'll hear back from my contact there soon and get that officially on the books. So again, I don't know if this is the week we're going to have it. I got to talk to the Oregon Caves people and get that all set up. But kind of the idea is probably on a Thursday for this class, right? We won't have class that morning. We'll have to drive out there and then go to the Oregon Caves. And it's like an hour 40 drive, right?
Which ones?
The Oregon Caves.
Yeah, there's like so many around here.
It's called the Oregon Caves. I don't know.
The ones out in like Cave Junction or?
Yeah, the Cave Junction
Oh,
one.
okay. Yeah, it's like an hour now.
It's a national monument. You guys are, yeah.
Do you have a rough idea of what day it will be?
Roughly we did it in like May of last year, so that's kind of what I'm shooting for, like a month out. But like I said, I'm trying to get the date nailed down with them like ASAP so I can tell y'all ASAP. Yeah. So unfortunately you do have to take yourselves, so that could involve like carpooling or something, so we can plan that, start thinking about that. If I need to do like a Google Forms thing of like who can drive and who needs a ride type thing, we can do that. But like I said, I need to get a date down, but I need to hear back from, so I know everything kind of gets backed up. But then we'll kind of switch gears. So kind of the last bit of the quarter is kind of more fun stuff, in my opinion. So we'll go back to radiochemistry. Well, I mean, it involves, carbon-14 is radioactive, but yeah, we'll talk about like other radioactive things again, because we did the rate laws with it. But we'll play with it, so we have a radioactive lab. And then we'll get into kind of OCHEM. So this is good prep if you're going on to OCHEM. We'll do some, I feel like this is a trivia chapter of transition metal chemistry, so we'll have some fun with that. Then back to organics. So again, just kind of thinking about laying out fundamentals for OCHEM, more OCHEM fundamentals, and so kind of end right with polymers, a little bit of biochem. So a little bit of everything this quarter. So if you're not crazy about the math, just hang in there, and we'll switch to less mathy things with rice tables at the end. And then kind of what's not on the syllabus is, I don't know like what student events are going on this quarter. So kind of historically we've done some like fun student events for extra credit. Uh-oh, why isn't my Wacom firing today? There we go. So I'll just say extra student events, question mark. So I don't know what's going on with student life. Like, I don't know if they'll have the same events. We used to do Earth Day, but Earth Day got accidentally nuked by a lack of funding. So that's probably not going to happen. That's okay. But there, last year there was like, does anybody remember there was like a cultural festival thing?
Yeah, I remember that.
What was it called? Do you remember?
I have no idea.
I'll just put cultural festival, question mark. Because last year I think I had my Chem 200 students make some ice cream. And we, of course, made cultural ice cream with different flavors. So I don't know if that's happening again. It would be fun if it's happening. I don't know. I don't know if any of y'all are more involved in student life. Blank. No. Well, anyways, we did that last year. I would love if we could do it again. I don't know what's going on. Or if you see like another student activity that like our class can get in on, like that would also be fun. So we can showcase, but anyways. All right, any other announcements or anything? So I will say, right, don't forget about your reading questions. So just going back to Blackboard here, so of the few things that are on there, I do still have your reading questions. So those are available, ready to go, so don't forget about them. There were quite a few people last quarter that lost a lot of points just by not doing stuff. And that's not helpful for the final grade later.
I guess I do have one question. What's usually like the next step as far as chemistry from here?
OChem.
Okay.
Yeah, so that's why we do a lot of OChem prep kind of at the end. Because, yeah, that's the next course directly after, so you'd be taking that probably at SOU or wherever else.
What kind of careers would you say like have a heavier focus on OChem? Okay, for me, environmental science. Would I be going in OChem at all?
You'd probably want to take OChem just so like you're more aware of the molecules in the background. Because, right, I think it just came out in the news that Bayer Monsanto just paid out some more money because of Roundup, right? So that's where you want to have some fundamentals so you can understand, you know, the chemistry, how those things accumulate in the soil and then end up, you know, in the person, obviously, or if they're exposed, you know, farm workers are exposed, obviously.
I assume OChem is offered in university, not here.
Yeah, so we don't offer OChem at RCC. I think so, the other instructor on Grants Pass, Sakar, he had like a pipe dream that of us offering it here, but I don't think it's realistic because if you remember from our SOU tour, right, you need fume hoods and all these things for working with organics. So yeah, we just don't have the facilities, so we would need more like fume hoods, and then the money starts going up very quickly running those fume hoods 24/7. So yeah, you can, like I said, most people end up taking it at SOU. I think you can dual enroll, if I remember. But yeah, otherwise you'll just transfer and take it at Oregon State or wherever you end up. All right, other questions?
Are you gonna have the lab PDFs on Blackboard?
Yeah, I will do that. I was just editing the PDF today. So yeah, the printout is there for y'all, and then I'll upload it when I get a chance. All right, so let's dive into the lecture. And so again, right, we're kind of continuing with our acids and bases. And so now let's look at antifreeze. And so antifreeze is, of course, a toxin to pets. I don't know if y'all are aware of that. And so, of course, the problem with antifreeze is it has ethylene glycol, and it tastes sweet. And so where might your pet be exposed to ethylene glycol or antifreeze? So, I mean, you have the car, but what else might be in your household? I mean, drain cleaner is not antifreeze, though.
Maybe like it was like old packs to put on yourself. No, never mind.
I don't know about the AC system. Snow globes. Yeah, snow globes are super dangerous. So if those things break, what's in them is antifreeze, ethylene glycol. So yeah, if your snow globe breaks, you would want to definitely keep, especially your cat, is what I hear. But yeah, keep your pets away from any broken snow globes, because if they go lick it, right, and then they would be obviously tempted to with this sweet taste, then they will get very ill and could die.
Does polyethylene glycol, is that classified as an alcohol?
Yeah, it would be an alcohol. And so the problem is that it's metabolized to this glycolic acid. And so then this glycolic acid ends up reacting with our hydrogen carbonate in our blood. So then, of course, that would drop the pH. And then that, of course, would affect the ability to carry O2. And so the treatment is to give ethyl alcohol, which has a higher affinity for the enzyme. So that could be a treatment if caught in time and able.
Is ethyl alcohol ethanol?
Yeah. And so like we were looking at, kind of our last thoughts last quarter was we were looking at these buffer solutions. And so just a reminder, we said there were solutions that resist a change in pH. And right, we either add a little bit of an acid or a base, and then our buffer, right, neutralizes whatever is added. So again, we're kind of thinking we're going to do the reaction. It's kind of setting ourselves up for the future. And then this is just a reminder of what the buffer must contain. So give me one example of a weak acid and a conjugate base. What's one buffer?
Citric acid.
So citric acid. And then what would be the conjugate base? Do you remember what citric acid's base form is called?
No.
So it'd be like probably sodium citrate. So citrate, and then I'm just going to put a counter ion. So Na3, and then obviously the true citric acid form. So good, right? So again, the idea, we have a weak base, and then we have, right, our salt. So then our salt is a base. What's a weak base and conjugate acid system we could use? What's our classic weak base? So water is more amphoteric. What's our other base? Kind of think back to Breaking Bad too. Not bromine. Bromide's neutral. What's our base? Plastic base, a cleaner, household cleaner.
Ammonium?
Yeah, ammonia. So ammonia, and then what's its conjugate acid, or an example?
Ammonium?
Yeah, so ammonium, and then I'll just make it a salt. So I just pick chloride. All right, so again, just kind of trying to put ourselves in the mindset there. So again, weak base, conjugate acid, thinking of equilibrium. And then, of course, we can think back to our blood system. So, of course, carbonic acid, and then our hydrogen carbonate. And so like we had left off with last quarter, we said that we have to have amounts of our weak acid and our base. And so we haven't really gotten into the math of all this, just kind of touching on it, okay. In this case, we have our acetic acid, and then, right, we're going to have acetate as our base. So mixing amounts of those. And so I'll kind of skip this text for now because I want to get to the examples of it. But basically, right, what we're trying to say is, let's say we're adding some base to our system. And again, we're thinking of our acetic acid now, sodium acetate buffer solution. And we're saying, okay, first, right, we need to do the neutralization reaction essentially. And then we can figure out, right, our change. And so again, same thing, if we add acid, we need to do essentially our neutralization reaction first and figure out, right, how much of our conjugate acid we made. And then obviously, right, equilibrium, so everything can shift back if necessary. And then so after the reaction, right, you have Le Chatelier's principle, of course. And obviously, right, we have our equilibrium. So it can go back and forth. All right, so then it kind of gets into this common ion effect. But in the back of your mind, I still want you to be thinking rice, right? So you're still going to use your equilibrium table. And so all we're saying is, okay, well, we have our system here. Again, we can be thinking of vinegar or acetic acid, so we can have some context. And right, again, sodium acetate, just thinking about that. And then basically what we're saying is, well, if we have a salt that obviously has our conjugate base, and it could be more sodium acetate, right? It doesn't really say. It could also be potassium acetate. And so then we'd have to, again, use our rice table, figure out how much we have, and then, of course, right, establish new equilibrium. And so the other thing that we can note is, right, we have different pHs, again, looking at our salts. And so it's just comparing if we put in, so of course this is just 0.1 molar of acetic acid here, and it's just showing it has a low pH of 2.9. Then it's saying, okay, if we just put in 0.1 molar solution of that conjugate base, then it's going to have, right, a basic pH 8.9, and then now this is showing us equal amounts of both. And so later we'll get into that this is kind of a special amount here. And, well, we'll save it. And so let's go through this one. But first I'll kind of let you think about how we might have to set it up again, right? We want to think about rice and kind of what we're saying. And so maybe just think about, right, how we would go about setting this up, kind of thinking about just how we do it right before even this confounding factor, right? We have, of course, our weak acid. I should probably give you the pKa at least. Let me see if I have that handy. Where's my seat? There it is. Okay, so pKa, that would help, is 4.74 for acetic acid. And I'll give you, that means the Ka is 1.82 times 10 to the negative fifth. So again, just kind of think about how you might set it up. So then before you get too into it, let's check on how we're doing. So right, you want to start with your reaction, just like we've done before. So our, right, acetic acid, and then this is just our Ka expression, right? So our acid plus water gives us hydronium. So again, just definition of our acid Ka plus our conjugate base. And so what's kind of maybe the difference from how we've done it before for our initial values? What do you notice, or what do we have to kind of put there for our initial values?
It's going to be 0.1 for the acetic acid.
Yep, so we have 0.1 of acetic acid, and then what else do we have?
And it's assumed we have water in excess, right?
Yeah, so water in excess, but then what else are we given initially?
Well, we're also given the pKa and the Ka, so we can use that to figure out how much of the hydronium gets produced.
And then, but before that though, because you said you had 0.1 molar of our acetic acid, but then what else do we have in our solution?
Would that be the sodium?
Yeah, so then we need to put that down too. And so that's one thing that's changed, right, from our kind of initial setups that, from what we've seen. So, okay, so now we're starting with acid, we're starting with base. And so notice, right, this is kind of, okay, we have these materials, but now we haven't done the equilibrium, the dissociation. And so our change is still going to be minus X. And then, right, since we haven't made any hydronium yet to start off with, then we have plus X, and then of course, right, this also has to be plus X. But it still should feel pretty familiar.
What about the water? Is that,
So remember, water's not included in the equilibrium expression. And so then, now we can kind of proceed like Hunter was saying. Okay, let's get our equilibrium. So 0.1 minus X. And we have X for hydronium. 0.1 plus X for our base. And then, just like we've done before, so we can plug it into our Ka expression. So hydronium times conjugate base over HA. And then, right, we said that was 1.82. if you were to look up this value, you might find a few discrepancies, so just be aware of that. And so then we can solve. So now this is looking like algebra time. And so what could we do here now to make our math easier? What do we remember?
Looks like you have a common factor right there, so you can just cancel that out and left with x. I know, because that's being subtracted right now.
Yeah, so we can't do that, but we could do another.
Because but 10 to the negative fifth, can we the equation simpler instead of x squared or something like that, just x?
Yeah, so basically we want to make the 5% assumption. So we're going to assume that x, the change, is less than 5%. And again, right, Lexi got that from this power here, so that was good, right? 10 to the minus 5, that's probably pretty small. Okay, so then we can just get rid of these x's, since again, right, we're saying this change is insignificant compared to this 0.1 value. So then that leaves us with easier math. So now we have x times 0.1 over 0.1. Oh, and that got even easier. So now we have x is equal to 1.82 times 10 to the negative fifth. And then we could check our 5% assumption. So check assumption. And I'm pretty sure it's going to check out with mental math, but I'll just plug it in the calculator for completion's sake. So 1.82 times 10 to the negative fifth divided by 0.1, and then times 100 to put it as a percentage. So yeah, 0.0182%, so really small. So yes, right, this is obviously less than 5%. So our assumption checked out. And so then last bit, now that we solved for x, right, we need to get our pH still. So now pH is just the negative log of our hydronium concentration. So negative log of x, which you can tell me what this is going to give me before you even plug it in.
Be like 4.7.
Yep, which is, do you recognize what that number is?
4.7.
Yeah, the pKa, exactly. So now we've now we're getting to where we want to get to. So okay, 4.74 roughly, which is yes, what we said the pKa was. Now we're getting to this relationship. And so before we get into stating kind of the obvious relationship, let's compare it. So now we want to compare to, and let's see, do you remember our Henderson-Hasselbalch equation from last time? I can write it up. So we have pH, and again, I'm going to use just a positive form, but there is the other form. So pKa plus the log, and that's just because I like base over acid. Keeps me sane for whatever reason. And so, of course, now let's plug in these values. So we said the pKa was 4.74 plus my log well, my acid and my base concentrations were the same, correct, in this problem. And so now we're kind of getting to the trick. So, right, if you have the log of two of the same things, right, it's 0. So we're saying basically if our HA in our buffer, right, if our acid equals our base concentration, then that means that our pH is just equal to the pKa.
What does pKa stand for again?
It's just a measure of like how disassociated it is. Remember, it's just the negative log of the Ka. So yeah, the lower the pKa, the stronger the acid. And then the higher the pKa gets, right, it's weaker, less favorable equilibrium. All right, excellent. So good job on that one. And so again, here's Henderson-Hasselbalch. And so this just gives us another method like we were exploring. Again, as long as we can take this X is small approximation. And so that's always a good check. So you don't always have to do rice. Yeah.
What powers did you say was like a good guess?
10 to like the -4 difference for sure. Usually 10 to the -3 ends up working out as well, but yeah. Once you get that difference. And so then this just kind of goes through the derivation of the Henderson-Hasselbalch, so you can at least appreciate that. So of course, we start with our Ka expression, just like before. And then, right, rearranged just algebraically to give it in terms of our hydronium. So hydronium equals our Ka times HA over A minus. Then take the log of both sides. So log of that, obviously this is equal to pH now. And so log, just kind of remember your log rules, right? Distribute, so dividing is the same as subtracting our log here. So we pulled out our Ka, distribute the negative sign. And so then negative sign. Okay, now we have log of hydronium is equal to our negative log of Ka, right? So this is just pH, pKa, and then this is our relationship. And so then by definition, we get pH equals pKa plus our log of base over acid. And so then we're just going to be kind of practicing that. And so again, right, ice or rice is always the best way to solve it. And right, it works under any condition. And then we can use Henderson-Hasselbalch again when we take this X is small approximation. And so it kind of gives us some, again, other guidelines. And so again, right, you're kind of comparing to your initial concentrations and then, right, our magnitude of Ka there. And so that's why I say, right, like 10 to the -3 magnitude, since you're looking at about 100 to at least 1,000 times larger. All right, so let's practice another one then. And so now we have our pH. So we have our buffer solution of a 0.05 molar benzoic acid solution and 0.15 molar of sodium benzoate. And so you're given your Ka there. So go ahead and try to solve it. I'd probably set it up by Rice, and then see if you can take an approximation, and then you can compare it to Henderson-Hasselbalch. And so that's probably something you would have to do on an exam, just kind of thinking about the exam, right, that you'll have to do it by Rice and then just kind of prove by Henderson-Hasselbalch that it's the same. So walk me through this a little bit. What do we put for our initial conditions?
0.05 concentration for the acid. And it's the 0.15 for the sodium benzoate.
So 0.15.
So if you wrote the sodium to not be there,
Oh,
is that because of the net ionic equation? That's what we're basing it off of?
Yeah, and I didn't really care, because, right, I don't care about the sodium. It could be potassium, could be lithium. We just care about the benzoate part. So, yeah, I left it off, but,
Okay.
yeah.
Okay.
But, yeah, you're kind of thinking about that, too, right? That it's like, okay, it's a salt, it's going to fully disassociate. So, yes, we'll have, right, 0.15 moles of our benzoate.
And then the change is going to be minus x.
So, minus x, and then
Plus x.
plus x, so that looks good. Then equilibrium.
Products over reactants.
Oops, come back.
This is also with the 5% rule.
So 5% rule. Okay, let me catch up to y'all. This sounds good though. So products. Let me just write it all out. And then 5% assumption, which is probably a good assumption from that -5 again. And so that really makes it easy then. So 0.15 over 0.05, so let me just plug that in. Oops. Oh, I can't do math apparently. Divided by 3. Ah. So then, do we get this for x? 2.16. I see some yeses. And so, pretty small number. So probably going to check out, but let's just do that. So 2 point, what did I say? 2 point, I'll round it, 2.17 then, times 10, the -5th. And then we probably want to check it with our smallest one, our 0.05 there. I think we'll still be in the clear. Put it as a percentage just to make it clear. Yep, so right, super tiny, 0.04%. So that worked out. So let me just, because again, on an exam, you just want to make it clear that yes, you checked it. So, okay, the assumption was correct. Otherwise, right, you'll have to go back and do some more painful math. And so then solving for pH, so negative log of our x. So about 4.66 or so for the pH, maybe 4.67 with rounding, so that's fine to have little discrepancies there. And then did we get a chance to plug it into Henderson-Hasselbalch yet? Right, yeah, take a minute or so to do that, and then we'll take our break. And we'll see, is it the same?
When you're doing the concentrations, is it like the initial concentration that you're looking at?
Yeah, so in this case, right, it is just the initial concentration because we're not doing any reactions, right? So we're just putting in, this is our weak acid base, this is our conjugate base, right? And then we just do it. Later on, we will have different scenarios, though, where we might have to do the reaction and then do the pH. So that's coming. How far up?
That's just fine. Okay, thank you.
Let's see, so what did we find? So we weren't given our pKa, so we had to solve for our pKa. So just negative log of our Ka. So don't forget that relationship. So then we're given about 4.19 plus our log, and of course, which one's our base, which one's our acid again? So 0.15, so base over acid. Excellent, so now plus my log, base over acid. And so did we get the same answer? So yes. And again, this also just kind of verifies that the 5% assumption was a valid assumption. And so we could just use our Henderson-Hasselbalch.
What's the relation to pKa and Ka? It's the negative log of it? Or?
Yeah, let me write it. Yeah, so the pKa is equal to the negative log of the Ka. All right, let's go ahead and take our 10-minute break or so. So be back around noon or 12:01. And so we'll keep practicing with this.
Yeah.
Yeah, it's statement of And I mean, sorry having such a degree, but this is for my yeah, and I think I sent such a message. I didn't know
What about your what?
you know to English returning what? So that was our class. Yeah, I think that was kind of cool. And so I did I needed a two homework about that and like a social science. So I think the statement performance is stupid. And then I would just need one more human piece in summer. So I'm just gonna take it in summer. Finish that off. Oh, that, yeah. Just take this number, the K. Yeah, the 221
Okay. And then once you put it to
Yeah.
I need orange.
That's true. I just like, alright.
Dang it.
Oh, I don't know.
Bleach has coffee.
Maybe you should. Yeah. Because I should know. Yeah. That's why genomics. Yeah. I try to keep I just got two red fingers. Yeah. So I still have a decent English lesson. And I know that. Like I still have a decent concentration. Because like how much she said. What? It's written down.
I'm like
Your advisor. Yeah.
You're like, what?
Yeah, I did. In November. Yeah, it's like. No. Fill you in? It looks like fill you in. Well, I'm in. Yeah, yeah. And there's no like. And then yeah. Just make sure you do the fun stuff and then. Oh, what's this?
Like a radio. I'm gonna go.
Yeah. You guys have a good time? Yeah, I love it. I don't know. He was so show.
Oh, yeah.
Yeah. I finally got a notebook.
Yeah, my dad-
I don't know if you saw it, but like the part of those pages kept ripping. Yeah. But this one's really nice. It doesn't bleed. So I like can't. You can see like that paper, but
Oh,
you can
yeah.
actually like write. Yeah. But I'm taking this off. Yeah. Yeah. Yeah, they don't
It's my Monday, I have.
Oh, really? Yeah. Yeah, I should have Yeah. Are you gonna do Well, I was just gonna.
She didn't have
If I'm gonna take it, I might as well do a calculus because the last one. That's what I'm doing.
All right, as we finish coming back from break, we can at least start on this one. So pH of our buffer solution. So we have some cyanic acid and potassium cyanide there is our buffer solution. And we have our Ka. And so again, just go through the equilibrium approach, right? Show the cancellation, show your X's small approximation, and then compare that to Henderson-Hasselbalch. So how are we doing on this? I just outlined kind of the setup for our first calculation. So I assume we got here, and then probably made some assumptions, given our 10 to the minus 10. So then I'll just keep kind of outlining the process. So again, just setting up with our KA expression.
Using the 5% rule, we can get rid of the added and subtracted x's on either side.
Excellent. So 5% assumption again. So then end up with x times 0.17 over 0.25 equals our KA. And so what do we get for x then?
I got 7.2 times 10 to the negative 10.
Times 10 to the negative 10, perfect. Does it sound good to other people? Okay, excellent. And so we could go ahead and just check it again for formality's sake, but again, we can already tell that's pretty small. And let's compare it to our smallest one. And obviously, this is going to obey the 5% rule, so 4.8 times 10 to the negative 7%. Yes, valid. Let me just again write it out so we can say, yes, we did it. What did I get? 4.8%. So yes, obviously way less than 5%. And then we can get our pH. So negative log of our x. Sorry, this looks like it should be 10. And so then did we get 9.14? Excellent. And then did we get a chance to plug it into Henderson-Hasselbalch yet, or?
I gave it a shot and I got the same answer.
Okay, so same answer. I think other people need a little bit more time. So let's finish. So let's see. So we're given at least the pKa this time. So I'm just writing out the formula again. So 9.31 plus our log. And now I forgot how much base and acid we had. Ooh, sorry, wild scrolling. So our base, so 0.17 over 0.25.
If you were to do this calculation with pKb instead of pKa, which is both the two coefficients, or
For Henderson-Hasselbalch, you
yeah,
mean?
would you then take the log of the acid over the base?
I would have to double check that formula. So yes, we get the same thing. All right, questions about this one? Yeah.
Can you scroll up a little real quick?
Oh, yeah. And zoom out too.
Thank you.
The notes should be syncing online, hopefully. Y'all can let me know if they're not. All right, so feeling good about this so far, buffers. All right, so now we're going to take it just to the slightly next level. And so first we're going to use our Henderson-Hasselbalch to calculate our pH. And so kind of towards your question, I don't have a formula with the pKb, but we have our relationship between Ka and Kb. So that's how I would approach it. And so let's see. So from last quarter, so we had this relationship, if you remember. We have Ka times Kb equals Kw. And if we need to go through this derivation again, we can. And then do we remember what Kw was?
7 or 14.
So maybe not, it's related to 14. So yeah, 1 times 10 to the negative 14. And yeah, you might be thinking of like the equilibrium point. There's like,
PKW would be 14, right?
the what?
PKW.
I don't think there's like a peak KW. But, because this is just our KW, right, water product constant. So that was 1 times 10 to the negative 14, thinking back to our pH scale. So then Ka times Kb equals Kw. And so while you were not given the Kb, right, you can figure out your Kb from your pKb and then get your Ka to plug into Henderson-Hasselbalch. So let's just start with that, the first step, and then we'll figure out how we're going to address part 2 there. And so in hindsight, I realized I should have given you this easier formula, which is just pKa plus pKb equals to 14. So you can get that from taking, right, the log of both of these sides. So log of two things multiplied is the same as two things added. And then taking the log of this gives us 14 here. Or just to prove a point, I did it the long way as well. So we can find our KB, right, by taking 10 to the negative power of our PKB. So I did that there first. So that's our KB. And then I plugged it into this expression. So dividing our KW constant by our KB. So that gives me my Ka. And then I took my log, so negative log of Ka, to give me back my pKa. But again, this was a much faster solution once you realize that. So you can use that next time. And so basically you should have gotten a pKa of 9.25. Did we get that at least? Okay, I see some nods. And so then we can use our usual Henderson-Hasselbalch of, again, pH equals our pKa plus my log of base over acid. And again, just keep straight in your mind who's your base. So obviously, right, this is our base. This is going to be our acid species in this case.
Could you, is it possible to combine the second half of this equation here? Like, say, you take the base, you find the molarity of the NaOH, and then add the two bases on top of that log calculation, or would that give you the wrong answer?
You're talking about like for the second part?
Yeah, it's 0.01 moles for molarity of the solution within 1 liter.
Yeah, so you could probably do what you're saying. But yeah, I just want to do it kind of step by step before we kind of jump there. But yeah, I think I see what you're saying. But yeah, just focusing on our calculation. So then we should get 9.25 plus 0.5 over 0.2. Oh, and I forgot to put log. Sorry. No. And so I get 9.68 for the pH then of this initial solution. So do we all get that from Henderson-Hasselbalch? Okay, some nods. Can ask questions now. Oh, sorry, question.
How did you find the
So the pKa, I went the long way and used this formula, but it would have been simpler if you had just gotten this relationship, pKa plus pKb equals 14. Otherwise, like I was showing, I went like the super long way and found my Kb first, so plugging in 10 to the negative Kb gives me my Kb expression. Then plugging it into here gives Ka. Take the negative log of that, gives me pKa.
Why did you write it to 9.68?
Oh, I don't know why I did. So 6.5 there. Sorry about that. All right, any other questions on this one? So now let's look at our second half of our problem. And again, I just want to take it kind of step by step. And so first, let's lay out our equation of, again, what's happening And we could write out our neutralization reaction that they want us to do. So basically, and I'm going to set it up, so we have our acid here, right? So again, I'm just kind of setting up for our reaction now. Let me change pen colors. So let's do, all right, so now we want to say, okay, let's set up for reaction. And so basically what I'm looking at is we're adding NaOH, right? So that's going to react with our acid species. So I'm just writing that step first, our reaction, right? So in this case, ammonium chloride, since again this is our acid, is going to react with sodium hydroxide to, and then, right, I'm just doing the neutralization. So it forms sodium chloride and then makes our base ammonia here. And of course, right, water, but I'm just not including water as part of our equilibrium expression. So that's kind of why I have it there. And so then the next part, so we have our reaction. And so now we probably want to convert everything to moles so we can actually do our reaction. And so now it says we have a pH of a 1 liter of a solution if, and so we're trying to also keep in mind our total volume for later. So, okay, we have 1 liter total, and then they told us that we added in 0.01 moles of solid NaOH. Okay, so in this case, we can just take the moles right at face value. We don't have to do any molarity moles calculation. So I'm just going to write that down. So 0.01 moles. Now I need to convert, right, these other amounts to moles. So again, now I'm looking at, so we were given a 0.2 molar solution. It's telling us we have 1 liter. So how many moles is that? Yep, so 0.2. And so again, so now I would write 0.2 moles for our initial condition since we were in molarity earlier, but now we need to be in moles for this reaction. And so how much base do we have initially as well? So, or check again, because right, we have 0.5 molar. So what is it? Yep, so 0.5. So 0.5 moles there. Excellent. And so now let's do our change, or kind of in this case, right, it's like almost our reaction now. So change, equilibrium, I'll put right, kind of react. So now let's react and do basically, right, our stoichiometry. So all our sodium hydroxide gets consumed. So after it reacts, right, it's going to be 0 moles. So these react, so then we can subtract, right? So 0.2 minus 0.01 moles. So I have 0.19 moles left of our acid. And so then, again, just looking at our stoichiometry, so if we consumed our 0.01 moles of sodium hydroxide, then we also made 0.01 moles of base, so plus 0.5 initially. So now we have 0.51 moles of ammonia. And so now we're basically at the home stretch. So do we feel okay about this? I just want to make sure we're all on the same page. Right, so again, just kind of recap in your mind what we did, right? First, we just put the initial conditions of everything, rewriting it in moles. Now we're reacting, and obviously, right, we have to have a smaller amount of base than acid. We can still overwhelm our buffer, so we won't be looking at situations like that. Or if we do, right, it'll be a titration. It'll be like we blew past the equivalence point, blah, blah, blah. So then all of our NaOH was consumed, right, do our moles. And so now what's the easiest way to solve our final pH? What can we plug this into? What's our formula we've been using? Yeah, Henderson, Hasselbalch. And so right now we have our moles of everything. We can, right, put it back in molarity, but notice, just kind of think about, so let's set up our Henderson, Hasselbalch. So we said our pH is pKa plus log of base over acid, right? And this should be in molar concentration, but this will work out just fine, right? So just kind of thinking about, we have 0.51 moles, but then we need to divide it by our volume, which is 1 liter. And notice it's pretty irrelevant, our volume now, since it cancels out anyways, so leaving you with your same ratio. But just keep that in mind, total volume, make sure nothing funky has happened. And so then we have pH 9.25 plus my log of 0.51 over 0.19. And so now I get 9.68 for our pH there. And then, right, we expected to not have changed a lot from our previous calculation. And so that's pretty much in line, right? We added a little bit of base, so pH went up just a little bit, but overall, right, not too significant in change. Questions? All right, so then let's just kind of go through a little bit of the theory background. And so now I'm just giving us some general thoughts and notes of how to make a buffer and obviously the capacity. And again, part of a buffer is that it's able to neutralize moderate amounts of acids or bases. Again, obviously, right, there's physical limitations. We cannot overwhelm the buffer. And so then we kind of have our buffering range at the pH at which our buffer is effective. And then our buffering capacity is just how much acid or base it can neutralize. And so, of course, the effectiveness depends on the relative amounts and then obviously absolute concentrations. That makes sense. And so a buffer is most effective when your base to acid ratio is 1, so equal concentrations of acid over base. That makes sense. You want large amounts of each. And then it's also effective, again, right, as long as the ratio between them is pretty similar. So, right, you want a good match of base and acid. And then obviously, right, the more moles you put in, then the more buffering capacity it has. And that's kind of obvious, right? Again, we're seeing that with the stoichiometry that like literally we just need more moles to be able to react.
Is that assuming like a monoprotic acid?
I mean, it would be, it doesn't necessarily matter if it's monoprotic or not, right? But you're still just thinking about you need more moles of it. Yeah. If it's polyprotic, then at least you have more buffering points, but yeah, you still want a large amount. And so again, obviously, more concentrated, more moles, they can react. And then, again, we want our ratio approaching 1 of our base to acid. And then it brings up this little caveat. Again, this would probably be for more specialized situations. But obviously, right, if you had a buffer that was generally going to deal with acid, then you might want to have more base to acid ratio and vice versa. But again, right, that's very situational dependent. All right, so now let's try to think through what this is going for and kind of how to calculate this. Again, maybe you want to think about Henderson-Hasselbalch. So what acid would we want to combine with its conjugate base salt to make a solution that's buffered at a pH of 4.25? And so calculate the ratio then of base to acid. So kind of think about that. How would you approach it? And we'll go over it. So what acid do you think would be the best candidate? And then where do we go from there to plug it in and solve? Yeah, where do we?
I would go for chlorous acid because it would form sodium chloride with the sodium. And its pH is low, so you have to use the least amount to reach equilibrium.
But you probably want to pick the acid, though, that has the closest pH to what we want. So I probably wouldn't pick chlorous acid. because they'll probably have to have a weird ratio too, because you want them, ideally, right, we want them close to 1:1.
That's formic acid.
Yep, so formic would be the better pick since, again, just absolute value, it's closest. Right, we didn't have anything at like 4.7, that's closer. So let's look at formic acid, and then we can plug it in right to Henderson-Hasselbalch. So pH equals pKa plus my log of base over acid. So now we're just trying to figure out, right, how much formic acid to formate then. And so now we can plug in some of these things. So we want 4.25. We have a pKa of 3.74. And now, again, we just need to get our ratio. So now just do the math. Now, did I do that correctly? Oh, no, I didn't. 4.25 minus. So now I have something, 0.51 is equal to the log base over acid. Get rid of logs, so 10 to the power is equal to base over acid. Now I got to plug in, so 10 power of 0.5. So we have 3.25 is equal to base over acid. So now we have, right, our ratio. So then we can say, or 3.24 I should have said with a rounding. So now we can say we need, right, 3.24 molar solution of base to, right, 1 molar solution of acid. So does that make sense there? Do we all get the ratio? So the important part, right, is that we just get our ratio. And then you can, of course, just always compare it to 1 molar, make it easy, right?
Can you scroll up just a little bit?
And then just make sure you're punching in on your calculator, all those good things, you're in base 10 and whatnot. All right. So we'll see how far we get with titrations. And so we've done titrations, but we're going to kind of keep doing titrations because we want to study these different points. And so, of course, blah, 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 we've kind of gone over that. We've done a basic titration. And so, again, right, things to keep in mind is we haven't changed our definition of our equivalence point. So again, equivalence point is just where our moles of hydronium equals moles of hydroxide. So something to keep in mind when we are asked to calculate various points. We've kind of talked about indicators. Again, we want to keep talking and thinking about indicators. And so, right, our main focus last quarter was just kind of on a basic titration. And by basic, I mean simple, right? So let's just say we have our thinking about when we titrated our sodium hydroxide with our citric acid, right? We just had our equivalence point, or really with KHP, because citric acid is triprotic, but then we want to kind of start thinking about other points. in our titration. So how is it going to be different when we titrate a weak acid with a strong base? And so we'll look at this. And so part of this next half of the chapter is kind of understanding what we have to do at each point, or where we are kind of on our titration curve to figure out our pH. So kind of looking at this, right, if we have a weak acid, so initially our pH is that of our weak acid solution. So again, right, we're just thinking equilibrium. And so again, right, this is just reminding us how we're going to approach it. And then before the equivalence point, and again, we'll go through all these calculations, but then right before the equivalence point, we're treating it like a buffer. And again, right, kind of thinking back to what we had to do in this problem, right? We did our reaction and then figured out our change in acid and base concentrations. And so that's all it's saying here, right, is we'll calculate our moles with our reaction stoichiometry and then probably use Henderson-Hasselbalch to get pH. And then this is another kind of key point, so half neutralization, right, again, where half of your thing is neutralized, then we're going to have our pH equals our pKa. And again, we'll look at that. And so this is kind of, if you were interested in capturing this, this is where, right, some sort of indicator at the pKa value could be helpful. Again, depending on kind of what titration you're doing. And then afterwards, right, then, or at the neutralization point, then you're just seeing how many moles is consumed, and then afterwards, right, it's like how much hydroxide is left over, and it's basically strong base at that point.
When you say half neutralization pH, what do you mean by that?
So when half of them are neutralized, right, so like if you're trying to neutralize your acid species, right, that means half of it, half the moles have been neutralized.
So would it be a pH of 7 altogether?
No, it's the pKa, because it's not at the equal point, it's the half equal point. But we'll go, like I said, we'll look at it in more detail. All right, we might be running out of time. Let's see how far we can get. So now we're looking at our problem here. And so at least see if we can set it up. We might have to leave the answer for next time. But we have 50 ml sample of 0.2 molar sodium hydroxide, and it's titrated with a 0.2 molar solution of nitric acid. And so just see if you can start the setup of the first part. So after adding 30 mils of our nitric acid, and again, just kind of paying attention. So this scenario that we're starting off with is, right, strong base, strong acid. So we just have to worry about our moles.
HNO3 is the same as nitric acid, right?
Yeah. So yeah, we'll probably save this for next time. I'll kind of at least tease where we're going. So, right, just start off with writing your reaction. So, of course, right, this is just a strong base neutralization reaction. I'm using my single arrow to show that we're not going to have back and forth equilibrium. But then initially, and I'll stop here, right, is we need to get our initial moles. And so you can chew over that. We'll probably warm up with this problem. So if you want to do some work on it, probably just want to start by calculating moles, right? Just good old reaction stoichiometry. All right, I will see you in lab then. So lab will continue the theme of titrations and all this good stuff. Then, of course, if you have any questions online, let me know.
Uh-oh.